Well, welcome. In this video I'm going to continue looking at the ballooning modes and how they can be used to, how we can solve for these modes and calculate the stability. Last video derived from the delta W equation. We showed that for narrow modes, so which are localized and so their gradients are large compared to the background, we can use the various orders in the delta W equation to first show that they must be long along the field lines. So the gradients along field lines must be small. And so therefore we're dealing with narrow modes which are small, localized across the magnetic field, and very long along the magnetic field. So in a torus, this kind of looks like modes where we have like a long, so this is the toroidal direction, for example, which in this video I'm going to label, this is going to be zeta, to avoid any confusion with phi as a field. So this is zeta is the toroidal direction, so the angle. And we have field lines which are going around this torus. So this is like the field line B is like along this. And we have modes which are narrow and small along here, so localized around a flux surface. And so the gradients, these are large compared to the background gradients. But the gradients along the fields are small. And so we have these kind of structures which are essentially elongated along the fields. So long and thin kind of tubes. And so we want a way of finding perturbations which are long along the field lines. We want perturbations which are narrow radially, and we want perturbations which are periodic. So if you go around this way, you should end up back where you started, and it's the same if you go around toroidally in zeta, you should end up back where you started. And it turns out that satisfying all these things at the same time is very difficult, and this is where the ballooning transform comes in really handy, because it's a way of automatically enforcing solutions to be periodic, and so it makes our life much easier when we're finding perturbations. So if we're looking for a function phi, so I'm going to call phi as this field which derived in the last video. It's essentially electrostatic potential or the perturbation, and this should be some function of the flux surface psi, the poloidal angle theta. So here, if this is like theta here, and then psi is the radial coordinate. I am using zeta to mean the toroidal angle. This should be the same if we then go either an n times around poloidally or m times around toroidally, should end up back at the same place. So this should be the same as where n and m are integers. Now in order to find solutions which are elongated along magnetic fields, it's really useful if we can have a coordinate system which is aligned to the magnetic field, because then we know which direction it is at any point in space, and we can choose solutions which are aligned to the magnetic field. And so you can use a field-aligned coordinate system. And if you see videos around lecture 8, we went through and introduced different coordinate systems. The basic idea is to choose two quantities which are constant along the field. And so in this case we have a coordinate alpha, which is related to the toroidal angle, as we'll see shortly. And then we have the radial coordinate. And so the idea is that on a single field line, alpha and psi are constant, and so therefore if we fix alpha and we fix psi, and we change the third coordinate, then we move along the field line. And so we can have a coordinate system where you have psi, alpha, and theta, for example, the poloidal angle, and then if we fix psi and alpha and we change theta, then we move along the field line. And here alpha is just given by the toroidal angle, zeta, minus q, which is the safety factor, times the poloidal angle theta. And so in this case, as theta is varied, we move along B. So we move around the magnetic field as theta is changed, keeping alpha and psi fixed. Okay, so this has some big advantages now that we have a coordinate system, so we can write our coordinates or our functions. So we can write it in terms of a kind of a psi, a theta and an alpha. And now that we know that the alpha is constant along field lines, this constant field lines, we can choose quantities which are smoothly varying and slowly varying along theta, and we automatically get something which is aligned to the magnetic field. The problem is that enforcing periodicity here is actually quite hard. So because our periodicity constraint becomes that we can go around in theta any number of times we want, and we should also need to shift in alpha, because alpha is now also a function of theta. Okay, so here we have the periodicity constraints that we have some function of phi, theta and alpha, and now we can go any number of times around in theta, but we need to subtract this quantity from alpha, which depends on q, and of course we can go around in the toroidal direction m times, and we should end up back where we started. So this is our constraint, and this is now much harder to enforce, particularly as q depends on psi. And so if we're looking at a function which depends on psi in the radial direction, this periodicity constraint is now a function of psi. And this same problem turns up when you look at the gradients of these functions. So if you take the gradient of alpha, for example, this is just the gradient of psi. That's pretty straightforward. But then here, because this q can depend on psi, you end up with so you have a q times grad theta, but you also have a term which is like theta, then you have dq by d psi, so q prime times grad psi. And now you can see if you go around 2 pi in theta, so if theta goes to theta plus 2 pi, then grad alpha goes to grad alpha minus this term, so 2 pi q prime grad psi. And so the coordinate system is not periodic, and this obviously causes problems when you're trying to write an equation in this coordinate system, and the coordinate system is not periodic, and so you need to enforce this periodicity sort of by hand, and this makes it very hard to enforce. So instead what we do is to use the ballooning transform, and what this does is it uses a function, and we essentially produce a function which, instead of going from 0 to 2 pi in theta, goes from minus infinity to plus infinity. And then we use the ballooning transform to create a new function which is periodic. And so this is quite a clever idea, and it makes the whole process much easier. So we're taking a function which is periodic in 0 to 2 pi in theta, and we're extending it from minus infinity to plus infinity. And what you can think about this as, instead of constructing something in a torus, we're constructing something along the field lines. And so in this coordinate system, theta is the parallel direction. And so as we increase theta, say we start here at this location, say theta equals 0. As we increase theta, go around the torus, and you'll end up back somewhere else. So it'll come back over here somewhere. And then as you go around the torus again, it'll come back to the location. And you can keep going around the torus, so you can keep increasing theta, and you'll just go around the machine. And of course you can go around the machine the other way if you increase theta. So if, say, plus theta is this way, minus theta might be that way. And so going from plus minus infinity in theta is like going along a field line. And so instead of thinking about this in terms of a poloidal angle, it's really a location along a field line. And so this theta direction is really along the field line. And so what we have is a perturbation. Let's say let's mark this as theta 0. We have a perturbation which is kind of very long. If we go, say, 2 pi in this direction, so this is minus 2 pi. So we've gone around the machine once in poloidal angle, but because of the field line pitch, we end up back at a different toroidal location, and so the amplitude of the mode hasn't decayed by then, so we can keep going around the machine. This might be minus 4 pi, and the same in the other direction we have here is like plus 2 pi and plus 4 pi. And so the field line wraps around the machine many times, and so we can just keep going off to minus infinity and plus infinity. And so we can create a mode which has some kind of envelope, and we don't have to worry about it being periodic in theta. And then what the ballooning transform does is we basically add together a whole load of these modes. So we just say that the function, which is a function of psi, theta, and alpha, is the sum over an infinite series, so it's minus infinity to infinity, of this function here. So if I call this is phi prime, for example, which is in minus infinity to plus infinity. So it's an infinite sum of, where L here is an integer, sum of all of the whole of these modes, all shifted by 2 pi. And so if I try and draw this, so it's the sum of a whole load of these modes. So I've just taken the same mode here, and then I've shifted it in plus 2 pi, plus 4 pi, and so on. So this will keep going, and the same for minus 2 pi, minus 4 pi. And so it's the sum of a whole load of these modes. And so the overall mode, it kind of looks a bit like this. So overall the mode has some kind of periodic part to it, and a constant part, but it's both periodic and long aligned to the field lines. So we end up with a mode structure which obeys at least two of the quantities we want. So it ends up being both periodic. So in theta and also in toroidal angle, and it's also elongated because we can choose the function here along the field line so that it's smoothly varying along theta, i.e. along the field line, and then by adding them up we can get a function which is periodic. Okay, so the next stage in the analysis is to look at Fourier modes. So in a tokamak, we can consider each toroidal mode number separate, and so we can write down that the function of, say, psi, theta, and alpha in this case, where here I've written n, here's the toroidal mode number. So we have a sinusoidal variation in toroidal angle. So remember, this alpha has toroidal angle inside, and so this is periodic along the toroidal direction, so we can Fourier transform along alpha. And so here we have a toroidal mode number, and the key here is to look at what happens at high n. So when n is large, what happens is that this exponent is rapidly varying, and so all the fast variation, so the steep gradients are in this part here, and this is a slowly varying so-called envelope function. And so this is a slowly varying, and so we've already seen that this function must be slowly varying along theta, because this corresponds to the parallel direction. It must also be slowly varying along psi, so we have a function with an envelope which is slowly varying, but then has a fast variation part, which is this part in here, and this partly comes from the Q shear. It gives us the localization of the mode. And so you can see this simplifies things considerably, because if you take a gradient of this field, say across the magnetic field, so what we get is that this, when you take derivative of this, because we can say that this is slowly varying part, and this is the fast varying part, when we take a derivative across the magnetic field, we just get this factor of minus in appearing here. So we just ignore the derivative of this part compared to the fast derivative of that part. And so here you have an in factor which appears. So here we have a minus in factor, and then we're just taking the gradient, so we end up with a gradient of alpha. And then this, the only thing it depends on anything here is q, which depends on psi. So we end up with a q prime times a gradient of psi, and then this e to the in factor here at the end. And then we can rearrange this here, so this factor in here, we can rearrange using the formula I had above. So where I derived this expression for grad alpha. So you see this term with grad alpha and q prime grad psi here. It's here almost there. So then we get this expression for the gradient of phi prime in terms of this quantity here. So we have a gradient of a toroidal angle and a q theta. What we do now is just shift, because we have periodicity constraints, we can just shift by 2 pi L and essentially just redefine this here as theta. And so here all these factors here have a theta plus 2 pi L. What you can see here is that this term here, so zeta minus q times this theta, this is just alpha. So this whole thing in brackets here, this is just alpha. And so if you put this back into the sum, so the phi is just the sum of these over all L's. What you find is just that grad phi, just some function of psi, theta, and alpha. Each term in the sum, so I'll look at the equation up here. So it's the sum over all of these expressions here. So if we take the gradient of this, each term in this equation just gets a minus in, and the grad alpha term appearing in here. And so the whole thing just becomes this in times grad alpha times our function here. And this means that then any gradient in our equations, any fast gradient across the magnetic fields, we can just replace with minus in grad alpha. In the same way, because we have a field line coordinate system, if we have a b dot grad phi, for example, then we end up with this is just, because b is grad alpha cross grad phi, this ends up just being 1 over j d phi by d theta. Theta is the poloidal angle. And so these are expressions for the parallel gradients of the perturbation field phi and the perpendicular gradients of the displacement phi. And so we can take our equation, like the ballooning mode equation, and essentially replace all perpendicular gradients with minus in grad alpha, and all parallel gradients with this 1 over j d by d theta. And in the last video, we derived this expression for ballooning modes from the delta W equation. So this is an equation for a scalar phi, which is the same phi we just worked with up here, and it's derived from the 0th order delta W equation, and tells us whether the mode is stable or unstable. So this is the equation for phi, which minimizes delta W, so for the most unstable mode. And so we can use these simplifications. So these parallel gradients, like b dot grad here and this b dot grad, so I'll just label this like this. So these are the slow derivatives along the field lines, and then the fast derivatives are this term here, which becomes this minus in grad alpha. These are, for example, this term here. This is a perpendicular derivative. These ones and this one. And so all the red ones here with the perpendicular gradients are replaced by minus in grad alpha, and all the parallel derivatives here are replaced by this. There's a bit of manipulating to do to get this, for example. So we have for the grad p cross b over b squared, and then here with this grad phi becomes a grad alpha. So we have a dot grad alpha term. So grad p is just dp by d psi times grad psi. So this bit here is p prime, which is dp by d psi times grad psi. So this is like a grad psi cross b dot alpha, and using the vector triple product, this just becomes, so we have a p prime over b squared for these constants out here. Then this just becomes a grad alpha cross grad psi dotted with b. And now this is just b. This is the definition of our coordinate system. This is b. And so here we have a b dot b, so b squared cancels with this one, and so here we just have a p prime. So this whole thing simplifies to p prime. And then we have this curvature term, so kappa crossed b dot b squared, and again this fast gradient here will become a dot grad alpha. So here we can just put in this formula, rearrange it a bit to put kappa on the outside, just using the vector triple product formula. And then we're going to substitute into here the expression for grad alpha, which I'll write out again. So there are now 3 parts to grad alpha, so it expands into grad psi perm, so the toroidal angle, and then the shear part, which has a grad psi. This part here, this factor is given various labels, something called S. This part here will then divide this kappa. This is a vector of the curvature. So kappa, if you remember, is b dot grad b. So it's the parallel gradient of the unit vector, and this can be divided into 2 parts. So this s dot kappa is going to be the normal component, so it's going to be the component which is across the magnetic field. So here we have this term b cross s dot kappa. That's going to be the component in psi, and then we have a component here which is b cross grad psi, which is going to be the binormal or geodesic curvature, because this is a curvature which is orthogonal to both the magnetic field and the radial coordinate, and so it's a curvature which is within the flux surface, and sometimes called geodesic curvature. And to write this more formally, we can write kappa as these 2 terms. So we have kappa psi, which is the normal. So this is the component essentially across the magnetic field, plus the binormal or geodesic curvature part. So here I'm calling S because I use this S here. And this is going to be in the S direction. And so fairly straightforward manipulation. You can get that if you have B, so B cross grad psi dotted with kappa. So this gives you basically a B squared, minus B squared times kappa S. And if you have a B cross S dot kappa, then this gives a b squared kappa psi. And so that's these 2 components here. So the result is that we can write this term, so kappa cross b dot grad alpha, we can write it in terms of these normal and geodesic curvatures as. And so now putting everything together, we have an expression for kappa cross b dot alpha dot grad alpha. Term for this grad p terms. This simplifies these expressions here. These become parallel gradients in theta, and this becomes a sort of n squared term with a grad alpha squared term. So here we have in squared. These terms each give an in factor, and so the in all squared term cancels out, and so what's left over is a simplified one-dimensional equation like this, which is the ballooning equation. So it's nice because it's a one-dimensional equation, so it only depends on theta. It's a scalar quantity phi, so it's phi which only depends on theta, and at least in this equation. So this is a 1D equation which can be integrated from theta is minus to plus infinity, and you can solve this on each flux surface separately. And calculate whether that mode is stable to high N ballooning modes. And so this gives an efficient way of calculating whether the plasma is stable or unstable to ballooning modes or to high N ballooning modes, because each flux surface can be tested independently. There's a trick actually for calculating whether this is stable or unstable, because what you're looking for is the difference between oscillating solutions and growing solutions. So if you remember, in ideal MHD, modes are either growing or they're oscillating. And so what you look for is modes here which have a zero crossing, so which cross the zero axis, and if you find a crossing, then it's unstable. And what you can do is very quickly calculate whether each flux surface is stable or unstable. And so numerically, this is quite a nice system.